In this presentation, we're going to look into the logic behind circuits that perform addition. Recall that our system of numbers use what's called positional weighting. Then a number like 1, 2, 3, 4. The 4 is in the ones place, the 3 is in the tens place, the 2 is in the hundreds place, the 1 is in the thousands place. So each number is weighted by a power of our base. This also brings up the related terminology of most significant and least significant. So in a number like 1, 2, 3, 4, the 1 is related to the highest power of 10 and therefore is considered to be the most significant digit, whereas the 4, being in the ones position, is the smallest power of 10 in the number and is the least significant digit. We are, of course, going to be adding binary numbers, but adding binary numbers and adding decimal numbers is very similar except for the change in base from 10 to 2. When we add decimal numbers, we look at a given position. Let's look at the ones position. We add the two numbers, 9 and 5, getting 14. And then we ask if that answer equal or exceeds the base. 10 in the case for decimal, it will be 2 for binary. It does. 14 exceeds 10. And so then we do a carry into the, in this case, tens place, and just keep the amount by which we exceeded the base, 4, in the ones place. Let's consider some terminology here. We are adding two numbers, so we are taking two numbers, we are performing some action and getting a new number. So a general term for performing some action is known as an operation. So we are performing the operation of addition. The numbers that are sort of the inputs to the operation are known as operands. And then in the case of addition, we are adding two pieces of data, two operands. And so this is known as a binary operation. Even when we are adding decimal numbers, it's a binary operation. So our addition is going to be binary in two senses. The operation will be binary, and then the numbers we're acting on will also be binary. Here we are looking at an example of binary addition. So in the ones place, we are adding 1 and 1, we get 2. So we put a 0 in the answer for the ones place, and we carry a 1. So now in the twos place, we have 1 and 1 and 1, which is 3. And that exceeds our base of 2 by 1. So in the twos place, we put a 1, and then we have a carried 1 shown in red up at the top of the fours place. In the fours place, we have 1 and 1 and 0, that is 2. So it does not exceed the base, it equals the base. So there's 0 in the fours place and a carried 1 into the eights place, etc. To make all the positions look alike, the 1s, 2s, 4s, 8s places, and so on, we're going to add a carry in the 1s place and then consider a carry out from our most significant digit. We're going to start to develop the logic of addition. We want to write it in terms of truth tables. And so the first question is how many inputs and how many outputs? So now we talked earlier about addition being a binary operation acting on two numbers. But now we're going to break it down into sort of one position at a time. And then we saw that when we are adding, say, in the fours place, there were the two digits in the fours place, but there might have been some carry from the twos place. Now we can perform the addition 2 digits at a time, so we can add the two numbers and then get an answer and then add in the possible carry. So that's a way to do it. And so we will consider either doing it sort of 2 digits at a time in sort of 2 passes, adding 2 numbers and then adding in the carry, or sort of doing it all at once. So that's what we'll be looking at in terms of our inputs. And then as we saw when we're dealing with the different positions of numbers, we always have 2 outputs. There's the sum, the answer that goes in that position as part of the answer, and then there's a carry output that goes to the next higher position. What we're looking at here is the truth table for the half adder. So this is ignoring for now the carry and just adding the 2 numbers. And so that means there are two inputs labeled here, A and B, with their four possibilities, 0, 0, 0, 1, 1, 0, and 1, 1. And then there are two outputs, the sum and the carry. So if we just go across row by row, 0 plus 0 is 0, and there's no carry. 0 plus 1 is 1, and there's no carry. 1 plus 0 is 1, and there's no carry. And 1 plus 1 in that position is going to give us a 0, and then there will be a carry. So we recognize these two truth tables. The sum is an excluded OR, one or the other, but not both. And the carry out is an AND. And so here we are looking at the gate version. The sum is an excluded OR, and the carry is an AND. So the previous logic, the half adder, adds two binary digits of a given position. But we know that once we consider all the positions, that we might have a carry in from the addition of the lower position. And so we need to sort of add one more thing. And so we go next to the full adder. So here we are showing making a full adder from two half adders. A half adder is an excluded OR and an AND, and you can see that I have two of them. They're shown in the sort of red dashed boxes there. And in the upper first one, we see that we are adding A and B, the digits from the given position. Let's imagine it's the fours place. So this is the fours place for number A and the fours place for number B. And we are adding them, and the result of the addition in the fours place comes out of the excluded OR. That gets fed into, as one of the inputs, into the second half adder along with the new input of the carry. So we take the sum from A and B and then again add that to the carry. And so then the overall sum, the sum out of the second half adder, is the overall sum. And then we have two carries. There could have been a carry from the first addition of A and B, or there could be a carry from the result of that being added to the carry-in output. And if either addition, either half addition, led to a carry-out, then we have a carry-out. So we take the two carry-outs and OR them. Instead of making the full adder from two half adders, we can also just sort of directly approach the full adder truth table, which is shown here. So it has three inputs, the A and the B, the numbers so that we are adding in this position, and some carry in from the lower position. And so we write out all the combinations. There are 8 of them. And then we write the sum and carry output for all those combinations. So I'll just talk about the first and last row. So in the beginning, we're adding 0, 0, and 0, which is a sum of 0 and a carry out of 0. And in the very last row down there, we are adding 1 and 1 and 1, which is 3. So there's a sum of 1 and then a carry out of 1. So we're going to put that full adder truth table into the Karnaugh style truth table to look for any possible simplification, and then we must do one output at a time. So here is the sum output. So we see in the Karnaugh style truth table for the sum output that there is no simplification. We have this checkerboard pattern of isolated ones, and we need ones next to each other to get simplification. So there are no simplifications. Now this is going to be represented by something that is going to look simple. We're going to say that it's a 3-input excluded OR gate. But it's just important that you understand that that's not a genuine simplification. It's just sort of a notational simplification. So here is the sum for the half adder. So we have the 2-input excluded OR. And to make it from scratch, you have 2 knots and 2 2-input ANDs and a 2-input OR gate, or you can represent it as an excluded OR. Now all we're really doing is hiding in that excluded OR gate all the contents of what you see to the left. So again, it's just sort of a sub-circuit kind of an idea, just sort of something that comes up, so we have a notation for it, but it's not a genuine simplification. And by a genuine simplification, I mean that you would save on logic, that there would be fewer transistors and take up less space and so on. So as we say, replacing two nots and two ands and an or with an excluded or is not a real simplification. It's like an apparent notational simplification, but not a real simplification, because a real simplification would be fewer numbers of transistors, and it's not that kind of genuine simplification. Another consideration is how many layers of gates or transistors must be passed through for it to start as an input and end up as an output. And that also is, in that sense of simplification, it is not a simplification. Now we turn our attention to the carry out output. And in the Karnaugh map, it is the following, and there are groups here, so there will be simplification. And we see a blue group there that is A, C, and the green group is A, B, and the red group is B, C. Or we can just identify it as a majority rules logic. And so here is the gate version of the full adder, starting from scratch rather than putting together two half adders. And so we see the carry out logic is the majority rules logic, 3 2-input ands and a 3-input or, and then the sum logic is a 3-input excluded or. So remember, that looks simple, but it's sort of hiding some complexity in there. As we said, one of the sort of real simplifications or real advantages is the number of layers of transistors or gates that must be passed through to get from input to output. And so on the left we have the full adder made from two half adders, and then on the right we have the sort of full adder made from scratch. And I want to talk about layers. And hidden in an excluded OR is 3 layers. There are nots, there are ands, there are ors. So that excluded OR represents sort of 3 layers of logic you must pass through. And to get to the final sum answer, you must pass through 2 excluded ORs if you take the half adder approach. And so that's 6 layers of gates that you must pass through. Whereas when you build it from scratch, as shown on the right, you have a 3-input excluded OR, and that's 3 layers of logic. So there are fewer layers of logic when you sort of build it from scratch, which is an additional genuine advantage.